Chapter 8 of Science and Hypothesis. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Science and Hypothesis by Henri PoincarÄ. Chapter 8. Energy and Thermodynamics. Energetics. The difficulties raised by the classical mechanics have led certain minds to prefer a new system which they call energetics. Energetics took its rise in consequence of the discovery of the principle of the conservation of energy. Helmholtz gave it its definite form. We begin by defining two quantities which play a fundamental part in this theory. They are kinetic energy, or vis viva, and potential energy. Every change that the bodies of nature can undergo is regulated by two experimental laws. First, the sum of the kinetic and potential energies is constant. This is the principle of the conservation of energy. Second, if a system of bodies is at A at the time t0 and at B at the time ti, it always passes from the first position to the second by such a path that the mean value of the difference between the two kinds of energy in the interval of time which separates the two epochs t0 and ti is a minimum. This is Hamilton's principle, and is one of the forms of the principle of least action. The energetic theory has the following advantages over the classical. First, it is less incomplete. That is to say, the principles of the conservation of energy and of Hamilton teach us more than the fundamental principles of the classical theory, and exclude certain motions which do not occur in nature and which would be compatible with the classical theory. Second, it frees us from the hypothesis of atoms, which it was almost impossible to avoid with the classical theory. But in its turn it raises fresh difficulties. The definitions of the two kinds of energy would raise difficulties almost as great as those of force and mass in the first system. However, we can get out of these difficulties more easily, at any rate in the simplest cases. Assume an isolated system formed of a certain number of material points. Assume that these points are acted upon by forces depending only on their relative position and their distances apart, and independent of their velocities. In virtue of the principle of the conservation of energy, there must be a function of forces. In this simple case, the enunciation of the principle of the conservation of energy is of extreme simplicity. A certain quantity, which may be determined by experiment, must remain constant. This quantity is the sum of two terms. The first depends only on the position of the material points, and is independent of their velocities. The second is proportional to the squares of these velocities. This decomposition can only take place in one way. The first of these terms, which I shall call U, will be potential energy. The second, which I shall call T, will be kinetic energy. It is true that if T plus U is constant, so is any function of T plus U, parentheses T plus U, and parentheses. But this function, parentheses t plus u and parentheses, will not be the sum of two terms, the one independent of the velocities and the other proportional to the square of the velocities. Among the functions which remain constant, there is only one which enjoys this property. It is t plus u, or a linear function of t plus u. It matters not which, since this linear function may always be reduced to t plus u by a change of unit and of origin. This, then, is what we call energy. The first term we shall call potential energy, and the second kinetic energy. The definition of the two kinds of energy may therefore be carried through without any ambiguity. So it is with the definition of mass. Kinetic energy, or vis viva, is expressed very simply by the aid of the masses, and of the relative velocities of all the material points with reference to one of them. These relative velocities may be observed, and when we have the expression of the kinetic energy as a function of these relative velocities, the coefficients of this expression will give us the masses. So in this simple case the fundamental ideas can be defined without difficulty. But the difficulties reappear in the more complicated cases, if the forces, instead of depending solely on the distances, depend also on the velocities. For example, Weber supposes the mutual action of two electric molecules to depend not only on their distance, but on their velocity and on their acceleration. If material points attracted each other according to an analogous law, u would depend on the velocity, and it might contain a term proportional to the square of the velocity. How can we detect among such terms those that arise from t or u? And how, therefore, can we distinguish the two parts of the energy? But there is more than this. How can we define energy itself? We have no more reason to take as our definition t plus u, rather than any function of t plus u, when the property which characterized t plus u has disappeared, namely that of being the sum of two terms of a particular form. But that is not all. We must take account not only of mechanical energy properly so called, but of the other forms of energy, heat, chemical energy, electrical energy, etc. The principle of the conservation of energy must be written T plus U plus Q equals a constant, where T is the sensible kinetic energy, U the potential energy of position depending only on the position of the bodies, Q the internal molecular energy under the thermal, chemical, or electrical form. This would be all right if the three terms were absolutely distinct. If T were proportional to the square of the velocities, U independent of these velocities and of the state of the bodies, Q independent of the velocities and of the positions of the bodies, and depending only on their internal state. The expression for the energy could be decomposed in one way only into three terms of this form. But this is not the case. Let us consider electrified bodies. The electrostatic energy due to their mutual action will evidently depend on their charge, that is, on their state, but it will equally depend on their position. If these bodies are in motion, they will act electrodynamically on one another, and the electrodynamic energy will depend not only on their state and their position, but on their velocities. We have, therefore, no means of making the selection of the terms which should form part of T and U and Q, and of separating the three parts of the energy. If T plus U plus Q is constant, the same is true of any function whatever, T plus U plus Q, end parentheses. If T plus U plus Q were of the particular form that I have suggested above, no ambiguity would ensue. Among the functions h T plus U plus Q, end parentheses, which remain constant, there is only one that would be of this particular form, namely the one which I would agree to call energy. But I have said this is not rigorously the case. Among the functions that remain constant, there is not one which can rigorously be placed in this particular form. How then can we choose from among them that which should be called energy? We have no longer any guide in our choice. Of the principle of the conservation of energy, there is nothing left then but an enunciation. There is something which remains constant. In this form it, in its turn, is outside the bounds of experiment and reduced to a kind of tautology. It is clear that if the world is governed by laws, there will be quantities which remain constant. Like Newton's laws, and for an analogous reason, the principle of the conservation of energy, being based on experiment, can no longer be invalidated by it. This discussion shows that, in passing from the classical system to the energetic, an advance has been made, but it shows at the same time that we have not advanced far enough. Another objection seems to be still more serious. The principle of least action is applicable to reversible phenomena, but it is by no means satisfactory as far as irreversible phenomena are concerned. Helmholtz attempted to extend it to this class of phenomena, but he did not and could not succeed. So far as this is concerned, all has yet to be done. The very enunciation of the principle of least action is objectionable. To move from one point to another, a material molecule, acted upon by no force, but compelled to move on a surface, will take as its path the geodesic line, that is, the shortest path. This molecule seems to know the point to which we want to take it, to foresee the time that it will take to reach it by such a path, and then to know how to choose the most convenient path. The enunciation of the principle presents it to us, so to speak, as a living and free entity. It is clear that it would be better to replace it by a less objectionable enunciation, one in which, as philosophers would say, final effects do not seem to be substituted for acting causes. Thermodynamics. The role of the two fundamental principles of thermodynamics becomes daily more important in all branches of natural philosophy. Abandoning the ambitious theories of 40 years ago, encumbered as they were with molecular hypotheses, we now try to rest on thermodynamics alone the entire edifice of mathematical physics. Will the two principles of Mayer and of Clausius assure to it foundations solid enough to last for some time? We all feel it, but whence does our confidence arise? An eminent physicist said to me one day, apropos of the law of errors, "Every one stoutly believes it, because mathematicians imagine that it is an effect of observation, and observers imagine that it is a mathematical theorem." And this was for a long time the case with the principle of the conservation of energy. It is no longer the same now. There is no one who does not know that it is an experimental fact. But then, who gives us the right of attributing to the principle itself more generality and more precision than to the experiments which have served to demonstrate it? This is asking if it is legitimate to generalize, as we do every day, empirical data, and I shall not be so foolhardy as to discuss this question, after so many philosophers have vainly tried to solve it. One thing alone is certain: if this permission were refused to us, science would not exist, or at least it would be reduced to a kind of inventory, to the ascertaining of isolated facts. It would no longer be to us of any value, since it could not satisfy our need of order and harmony, and because it would be at the same time incapable of prediction. As the circumstances which have preceded any fact whatever will never again, in all probability, be simultaneously reproduced, we already require a first generalization to predict whether the fact will be renewed as soon as the least of these circumstances is changed. But every proposition may be generalized in an infinite number of ways. Among all possible generalizations we must choose, and we cannot but choose, the simplest. We are therefore led to adopt the same course as if a simple law were, other things being equal, more probable than a complex law. A century ago it was frankly confessed and proclaimed abroad that nature loves simplicity, but nature has proved the contrary since then on more than one occasion. We no longer confess this tendency, and we only keep of it what is indispensable, so that science may not become impossible. In formulating a general, simple, and formal law, based on a comparatively small number of not altogether consistent experiments, we have only obeyed a necessity from which the human mind cannot free itself. But there is something more, and that is why I dwell on this topic. No one doubts that Mayer's principle is not called upon to survive all the particular laws from which it was deduced, in the same way that Newton's law has survived the laws of Kepler from which it was derived, and which are no longer anything but approximations, if we take perturbations into account. Now why does this principle thus occupy a kind of privileged position among physical laws? There are many reasons for that. At the outset we think that we cannot reject it, or even doubt its absolute rigor, without admitting the possibility of perpetual motion. We certainly feel distrust at such a prospect, and we believe ourselves less rash in affirming it than in denying it. That perhaps is not quite accurate. The impossibility of perpetual motion only implies the conservation of energy for reversible phenomena. The imposing simplicity of Mayer's principle equally contributes to strengthen our faith. In a law immediately deduced from experiments, such as Mariott's law, this simplicity would rather appear to us a reason for distrust, but here this is no longer the case. We take elements which at the first glance are unconnected. These arrange themselves in an unexpected order, and form a harmonious whole. We cannot believe that this unexpected harmony is a mere result of chance. Our conquest appears to be valuable to us in proportion to the efforts it has cost, and we feel the more certain of having snatched its true secret from nature in proportion as nature has appeared more jealous of our attempts to discover it. But these are only small reasons. Before we raise Mayer's law to the dignity of an absolute principle, a deeper discussion is necessary. But if we embark on this discussion, we see that this absolute principle is not even easy to enunciate. In every particular case we clearly see what energy is, and we can give it at least a provisory definition, but it is impossible to find a general definition of it. If we wish to enunciate the principle in all its generality, and apply it to the universe, we see it vanish, so to speak, and nothing is left but this: there is something which remains constant. But has this a meaning? In the determinist hypothesis, the state of the universe is determined by an extremely large number n of parameters, which I shall call x1, x2, x3, and so on to xn. As soon as we know at a given moment the values of these n parameters, we also know their derivatives with respect to time, and we can therefore calculate the values of these same parameters at an anterior or ulterior moment. In other words, these n parameters specify n differential equations of the first order. These equations have it n-1 integrals, and therefore there is n-1 functions of x1, x2, x3, etc. to xn, which remain constant. If we say, then, there is something which remains constant, we are only enunciating a tautology. We would be even embarrassed to decide which among our integrals is that which should retain the name of energy. Besides, it is not in this sense that Mayer's principle is understood when it is applied to a limited system. We admit, then, that p of our n parameters vary independently, so that we have only n minus p relations, generally linear, between our n parameters and their derivatives. Suppose, for the sake of simplicity, that the sum of the work done by the external forces is zero, as well as that of all the quantities of heat given off from the interior. What will then be the meaning of our principle? There is a combination of these n minus p relations of which the first member is an exact differential, and then this differential vanishing in virtue of our n minus p relations, its integral is a constant, and it is this integral that we call energy. But how can it be that there are several parameters whose variations are independent? That can only take place in the case of external forces, although we have supposed, for the sake of simplicity, that the algebraic sum of all the work done by these forces has vanished. If, in fact, the system were completely isolated from all external action, the values of our n parameters at any given moment would suffice to determine the state of the system at any ulterior moment whatever, provided that we still clung to the determinist hypothesis. We should therefore fall back on the same difficulty as before. If the future state of the system is not entirely determined by its present state, it is because it further depends on the state of bodies external to the system. But then, is it likely that there exist among the parameters x, which define the state of the system of equations, independent of this state of the external bodies? And if, in certain cases, we think we can find them, is it not only because of our ignorance, and because the influence of these bodies is too weak for our experiment to be able to detect it? If the system is not regarded as completely isolated, it is probable that the rigorously exact expression of its internal energy will depend upon the state of the external bodies. Again, I have supposed above that the sum of all the external work is zero, and if we wish to be free from this rather artificial restriction, the enunciation becomes still more difficult. To formulate Mayer's principle by giving it an absolute meaning, we must extend it to the whole universe, and then we find ourselves face to face with the very difficulty we have endeavored to avoid. To sum up, and to use ordinary language, the law of the conservation of energy can have only one significance, because there is in it a property common to all possible properties. But in the determinist hypothesis there is only one possible, and then the law has no meaning. In the indeterminist hypothesis, on the other hand, it would have a meaning even if we wished to regard it in an absolute sense. It would appear as a limitation imposed on freedom. But this word warns me that I am wandering from the subject, and that I am leaving the domain of mathematics and physics. I check myself, therefore, and I wish to retain only one impression of the whole of this discussion, and that is, that Mayer's law is a form subtle enough for us to be able to put into it almost anything we like. I do not mean by that it corresponds to no objective reality, no, that it is reduced to mere tautology, since in each particular case, and provided we do not wish to extend it to the absolute, it has a perfectly clear meaning. This subtlety is a reason for believing that it will last long, and as, on the other hand, it will only disappear to be blended in a higher harmony, we may work with confidence and utilize it, certain beforehand that our work will not be lost. Almost everything that I have just said applies to the principle of Clausius. What distinguishes it is that it is expressed by an inequality. It will be said, perhaps, that it is the same with all physical laws, since their precision is always limited by errors of observation. But they at least claim to be first approximations, and we hope to replace them little by more exact laws. If, on the other hand, the principle of Clausius reduces to an inequality, this is not caused by the imperfection of our means of observation, but by the very nature of the question. General conclusions on Part 3. The principles of mechanics are therefore presented to us under two different aspects. On the one hand, there are truths founded on experiment, and verified approximately as far as almost isolated systems are concerned. On the other hand, there are postulates applicable to the whole of the universe and regarded as rigorously true. If these postulates possess a generality and a certainty which falsify the experimental truths from which they were deduced, it is because they reduce in final analysis to a simple convention that we have a right to make, because we are certain beforehand that no experiment can contradict it. This convention, however, is not absolutely arbitrary. It is not the child of our caprice. We admit it because certain experiments have shown us that it will be convenient, and thus is explained how experiment has built up the principles of mechanics, and why, moreover, it cannot reverse them. Take a comparison with geometry. The fundamental propositions of geometry, for instance Euclid's postulate, are only conventions, and it is quite as unreasonable to ask if they are true or false as to ask if the metric system is true or false. Only these conventions are convenient, and there are certain experiments which prove it to us. At the first glance the analogy is complete. The role of experiment seems the same. We shall therefore be tempted to say, either mechanics must be looked upon as experimental science, and then it should be the same with geometry, or, on the contrary, geometry is a deductive science, and then we can say the same of mechanics. Such a conclusion would be illegitimate. The experiments which have led us to adopt as more convenient the fundamental conventions of geometry refer to bodies which have nothing in common with those that are studied by geometry. They refer to the properties of solid bodies and to the propagation of light in a straight line. These are mechanical, optical experiments. In no way can they be regarded as geometrical experiments. And even the probable reason why our geometry seems convenient to us is that our bodies, our hands, and our limbs enjoy the properties of solid bodies. Our fundamental experiments are preeminently physiological experiments, which refer not to the space which is the object that geometry must study, but to our body, that is to say, to the instrument which we use for that study. On the other hand, the fundamental conventions of mechanics and the experiments which prove to us that they are convenient certainly refer to the same objects or to analogous objects. Conventional and general principles are the natural and direct generalizations of experimental and particular principles. Let it not be said that I am thus tracing artificial frontiers between the sciences, that I am separating by a barrier geometry properly so called from the study of solid bodies. I might just as well raise a barrier between experimental mechanics and the conventional mechanics of general principles. Who does not see, in fact, that by separating these two sciences we mutilate both, and that what will remain of the conventional mechanics when it is isolated will be but very little, and can in no way be compared with that grand body of doctrine which is called geometry? We now understand why the teaching of mechanics should remain experimental. Thus only can we be made to understand the genesis of the science, and that is indispensable for a complete knowledge of the science itself. Besides, if we study mechanics, it is in order to apply it, and we can only apply it if it remains objective. Now, as we have seen, when principles gain in generality and certainty, they lose in objectivity. It is therefore especially with the objective side of principles that we must be early familiarized, and this can only be by passing from the particular to the general, instead of from the general to the particular. Principles are conventions and definitions in disguise. They are, however, deduced from experimental laws, and these laws have, so to speak, been erected into principles to which our mind attributes an absolute value. Some philosophers have generalized far too much. They have thought that the principles were the whole of science, and therefore that the whole of science was conventional. This paradoxical doctrine, which is called nominalism, cannot stand examination. How can a law become a principle? It expressed a relation between two real terms, A and B, but it was not rigorously true, it was only approximate. We introduce arbitrarily an intermediate term C, more or less imaginary, and C is, by definition, that which has with A exactly the relation expressed by the law. So our law is decomposed into an absolute and rigorous principle which expresses the relation of A to C, and an approximate experimental and revisable law which expresses the relation of C to B. But it is clear that however far this decomposition may be carried, laws will always remain. We shall now enter into the domain of laws properly so called. End of Chapter 8.